written homework? Okay, good. So first order linear differential equation you will solve using integrating factor. Now this one is little different, but it's a separable differential equation here. It has a lot of features, and if we start understanding this differential equation in depth, it will take us some time. So let's understand this differential equation. First of all, the right hand side has certain has a name also. So when we write this type of differential equation, y prime equals to this, y prime means what? Y prime physically dy over dx, right? And it's a so what is unknown here? Function y. That's what we are looking for. And dy over dx will mean a derivative of that function at certain point. So suppose you get a graph of a function and then you are trying to look at a derivative at certain point at that graph, that will be given by this expression. So that means dy over dx is physically a slope at a point. So this side represents slope of a solution curve at every point. Now we want to solve this, so if we try to understand, this can be splitted up into fx and gy function, where fx is just 1 and gy is y times 5 minus y. Now in order to solve this differential equation, I will separate first because it's a separable. So first step will be dy over gy is equals to dx, which will be nothing but dy over y times 5 minus y equals to dx. So now, since I am dividing this dy with this, I am imposing certain condition here. I am assuming something. What I am assuming here? When can I divide by a certain function? I am assuming that what is non-zero?
That y is not 0 or it's not 5.
Exactly right. Very good. So we are assuming y non-zero and y not equals to 5. Because if it is equals to 5 or 0, then we cannot divide. Okay, but if we look at this differential equation, is y equals to 0 a solution of this differential equation? Right hand side, when y is 0, right hand side will be just 0, right? And what about left hand side? Derivative of constant is 0. So 0 is satisfying this. 5 is also satisfying this differential equation. So 0 and 5 are the solution of this differential equation, and they are called a singular solution. Okay. So note, y equals to 0 as per our previous our singular solution. Previous lecture, they are singular solution. Okay, we basically, now we are not focusing on them and we are just thinking about what are all other solutions. So now I will integrate both the sides. This equation 1. So I will get, how will I integrate this? Dy over y times 5 minus y. This is x plus constant. But what about the integration of this? Dy over y times 5 minus y. So carry 2. How to differentiate multiplication of two function in the denominator. Denominator is a higher degree polynomial. Numerator, it's 0 degree. So what is the trick? What should we do at this point if we want to integrate this? I I cannot do ln of something because it's y times phi minus y. Partial fractions. Okay, we will decompose this into a partial fractions. So using partial fractions, we have to write down this as a over y dy plus b over 5 minus y dy x plus c. Now if I am able to get the value of a and b, then it's simply this ln of that and ln of this expression with absolute sign. So what are a and b here? So dy over, so basically it is nothing but what we are trying to do here is 1 over y 5 minus y should be equals to common denominator, then it will be a times 5 minus y plus b times y and whole thing divided by y times 5 minus y. So is this step clear to everyone? Any question in this step? It's 1 over, right, 1 times dy, so it's 1 over this thing. It should be equals to the splitting. Now that means denominators are same, so 1 has to be equals to a times 5 minus y plus b times y. So comparing the coefficients, we will get so constants here is 5a, coefficient of y is negative a plus b. So negative a plus b has to be, coefficient of y is negative a plus b, and on the left hand side we don't have y term. So negative a plus b has to be what? 0. And then 5a has to be 1. So that means a is 1/5 and therefore b has to be b also has to be 1/5, right? Because minus a plus b is 0. So b is equals to a, so b has to be 1/5. Okay, plug this value back in this expression and simplify it. So you will get here 1 over 5 ln of absolute of y. Now you have a negative sign here in front of y, so it will be negative 1 over 5 ln of 5 minus y is equals to x plus constant of integration. You can further simplify it. It can be written as 1 over 5 ln of y over 5 minus y with the absolute sign x plus c. So what are the initial conditions in this problem? Y at 0 is 2. So let's apply those initial conditions to graph C. So if y is 2 at x equals to 0, that means 2 over 3, right? 1/5 of ln of 2/3 is equals to 0 plus c. So c, this will imply c is nothing but 1/5 of ln of 2/3. Now at this point I would say there is lot in this differential equation. Okay, now let's start understanding. I have to remove this absolute sign. If y is negative, then we will get different solution. If y is positive, we get different solution. If y is less than 5, we get different solution. If y is bigger than 5, we get different sign. Right? So there is so many things coming up here. So how we will understand this? So let's go back first of all and understand what is mean by y prime equals to 0. So we have differential equation 5 minus y, right? If y prime is 0, if I equate this to 0, what does it mean? It's flat, right? Constant. Solution is constant. So y equals to 5 and y equals to 0 are the points such that if I start with my initial condition at that particular point, then I will stay at that point. So let's try to understand it geometrically. So y is equals to 0 means this x-axis. So x-axis is a solution. Y equals to 5 is also a solution. Now what is happening now inside this region above y equals to 5, below y equals to 0? How will the solution curve look like apart from these? Now one thing is very important about solution trajectories, that they don't cross each other. Solution trajectories will never cross each other. So if y equals to 5 is a solution, and if there is a solution in between, it cannot cross y equals to 5 and go up. It will be trapped inside it. And if there is a solution below y equals to 0, it will not cross y equals to 0, it will be trapped below it. So another remark, solution curves, or you can say there is another name for them, integral curves. Solution curves do not cross each other. Now if they don't cross each other, we have to still understand what is happening here. Now if y is less than 5, that means this thing will remain positive, right? 5 minus y. And since y is bigger than 0, this will remain positive. Correct? Because this was the last form of a solution we derived. So if we are in this region, then it will be 1 over 5 ln of y over 5 minus y, and I can get rid of this absolute sign. Is this making sense to everyone? Okay, so let's just then in this region we have 1 over 5 ln of y over 5 minus y is equals to x plus 1 over 5 ln of 2/3. So simplifying it a little bit more, 1 over 5 ln of y over 5 minus y, and I am subtracting this term here, so it will be flipped. So I have to divide this by 2 over 3. Right? Because if this term goes on the left, it would be minus 1 over 5 ln of 2 over 3. ln a minus ln b is ln of a over b. So it will be this, and this has to be equals to x. This will further imply, more little bit simplifying. So we have here 3y over 10 minus 2y is equals to e to the power 5x. We can simplify for y, and that would be in terms of x, and that's how solution trajectory will behave here in this region. Below y equals to 0, this term is negative, right? This term, what will happen to this one? If y is negative, this is positive. So we will get rid of mod with keeping a negative sign in front of y. Because if it's a negative, negative, negative will make it positive, right? So you know this definition of absolute of y will be y if y is positive or equals to 0, and negative y if y is 0, less than 0, because eventually we want a positive outcome of absolute sign. So since we want positive outcome, so if it is negative, negative will become a positive, and this is positive. So making sense to everyone? Is or no? So if y is below 0, like here, below 0, then solution will be, we will be taking the same expression, but we will be redefining it. So we will get here, now in this scenario we will have 1 over 5, now this will become negative y, 5 minus y stays as it is, and x plus 1 over 5 ln of 2/3. So now we will keep this negative sign here, and then we will simplify by exponentiating and all that, simplify to get y. Above y equals to 5, we will have both positive, y also and this also. So this will be the same way the solution will behave as we have figured out here. Okay, now since it is not crossing, and solution, how does it look like? If we just little bit do some work and simplify this, we will be having what here? So this would be 10 e to the power 5x So we will have here 3y equals to 10 e to the power 5x, and then we have minus 2y e to the power 5x. So that means 3 times, let's take y out. So y is 3 plus 2 e to the power 5x is equals to 10 e to the power 5x. So that means y of x solution will look like, now is it increasing, is it decreasing, what is happening to this curve? We try to see the sketch of this graph. How will it look like? 10 e to the power 5x over 3 plus 2 e to the power 5x. So obviously this is just a translation to the exponential function here, and if we see the scaling part here, this is just 5 times the numerator. So this function will be what? So what I want to now convey here is, will it be asymptotic to any of these x's? Because it will not cross it. But how is going to trap inside it? What will happen when x approaches to infinity? So what is the limit as x approaches to infinity in this expression? It's infinity over infinity form. So L'Hopital's rule you can apply, right? So you will get what? 50. You will get 50 e to the power 5x divided by 10 e to the power 5x, right? Calculus. So this, if you try to understand what is limit x approaches to infinity of this yx. So your numerator is approaching to infinity, denominator is approaching to infinity. So using L'Hopital's rule, you will have here derivative of numerator will be 50 e to the power 5x, denominator will be 10 e to the power 5x, e to the power 5x gone, limit will approach to 5. So yx will approach towards 5, the curve. So this solution curve which will lie between this region has to go towards 5. So it will be like touching like this. It will be going closer and closer to 5 here. So this whole equation, it has a physical interpretation which is called as logistic equation. It is used to model population. It was a crude model given initially. Now, as you can see, 5y is initiating in the growth of population because of constant times y, but negative times 5y square is decreasing the population, right? If you try to understand here, 5 times y minus y square is decreasing the population. So there is death, there is lack of food, or lot of factors, lack of space could be there, by which population could be decreased, and population is increasing with just linearly here in this differential equation. It was a crude model, but first, I think after Malthusian, this model came. First was Malthusian, and then it was logistic equation. Okay, so now there is a name for these solutions, and if I give my initial condition at y at any value of x is equals to 5, then I will stay only on this solution. I will not go anywhere. So if I impose a condition in the above differential equation, y at 3 is equals to 5, then the solution of this differential equation is y equals to 5 only. You don't even have to solve the differential equation. So you have to be careful. Seeing a problem, if y prime is 0 at that point, solution, if you start at there, you will stay at there. So those are also called as equilibrium points. If you start at that position, you will stay at that position, because your initial condition, if I give your initial condition here in this problem, y at 3 is 5 to this differential equation, then solution to this differential equation is 5. That's it. You don't have to do anything. Unique solution, because we are looking for. And if I give y at some value as 0, then it will be 0. That's it. No need of solving it. So, in order to find equilibrium, the point where you start, you stay at that point. You always equate y prime equals to 0 and solve for values of y. Those are called equilibrium points. Now, to understand whether that equilibrium point is stable, unstable, or a saddle, this is the 3 features of a point. Stable means if you start at that point, in long term you will come to that point. Or if you start close to that point, you will sink in that point. So, all the points where y prime is equals to 0 are called as equilibrium point. Now this theory is useful when we try to understand what will happen to solution eventually. If we are trying to understand the solution in a short interval of time, we can just explicitly give this expression. But if we want to understand what will happen to the solution eventually, we need to understand this theory of whether the solution we are starting is a closer to equilibrium point and whether that point is stable or unstable. So what happens if point is stable, so there are 3 categories of this point. Equilibrium point can be stable, can be unstable, and it can be saddle point. 3 possibilities of an equilibrium point. Okay, so when do we call an equilibrium point stable? If we start close to the equilibrium point and eventually as time approaches to infinity, we get to that point. So it can be, suppose if this is my equilibrium point, and if I start closer, my solution trajectories move round and round and round and round, and it goes sink into that point in infinite time. This situation, if the arrow is going inside, then it will be a stable scenario. So you are basically going inside to the point, and this point here is equilibrium point. So in 2D you started out with somewhere here, initial, and then you went towards this point. So this point will be stable. If you start closer and somehow you moved away from the point, that would be unstable situation. You are kind of spiraling outward. You are moving away from the point. That's unstable. Saddle will be so this is okay, stable situation. Unstable will be you start at here, say, and you are moving outward to this point, outside, and out you are going outside. So it's unstable. Saddle will be like a horse saddle. So if you are thinking in the 2-dimension case, one axis is pushing towards itself, where another axis will be pushing away. So if you are solution curve is starting here, and if you get closer, then you move away, and in this equilibrium is my origin. And if you are getting closer to the equilibrium, you get pushed away by another axis. So this is saddle situation. One axis will be pushing towards, another will be repelling it. One is attracting, another is repelling. This is saddle situation. It's not like it comes closer, but then it's pushed away. Here it gets inside, and here it will spiral outward. Now in above previous differential equation, if y equals to 5 and y equals to 0 are equilibrium point, then what are they? Are they stable or are they unstable? So for y prime equals to y times 5 minus y equals to 0 and y equals to 5 are equilibrium points. We want to understand whether y equals to 0 is stable or unstable. Okay, so how will you figure it out? So I told you the situation of how they might be doing it, but now the question is, how will you exactly figure it out whether it's a stable or unstable? So what happens to the slope? So y equals to 0. If I start close to 0, will I move towards 0 or will I be pushed away from 0? And if I am starting close to 5, will I be pushed towards 5 or will I go away from 5? So previous explicit computation told us what? If we are close to 5, we will be so here we did calculation here, and this region we were in the region here. Solution curve was given, and I also told you when y is bigger than 5, you will get exact same expression for that as well, because y will be positive and 5 minus y will be. What will happen to that? So if I am here, I will go towards 5. But if I am above 5, where will I go? Yeah, if I am here, then I will go towards 5. But if I am above 5, where will I go? That's one question. Now coming back to y equals to 0. if this expression here we have, oops, right. So by the nature of slope you can figure it out, how you whether it's a stable or unstable. So let's do another way out. So solution definitely is telling you, but you know what, I also want to show you one thing. So let me pull that up very quickly. So suppose this is a software which you will be using for okay, it's asking my, no, I don't want to go through this one. So Rice P-Plane. Rice P-Plane is basically a software developed by Rice University Professor John Poking, and it's a nice piece of software which can be used to figure out how a solution will behave. So if I go to this one, and you can download this on your computer, they do have MATLAB version as well. Let me see if I do have on my desktop. Okay, let me see. I think I do have it. Here it is. So this one, this is basically like y prime equals to that kind of setting, the same one, but here they have inbuilt variable as x, so we will treat x to be like our y, and then f is a slope. So here instead of t, I will use x, so I will have here x times x minus 5, because y prime is y times y minus 5, right? That was the differential equation. And what was the range of the time? Maybe let's take it equally spaced. Now you can see at 0, if I start here where my cursor is, if I click on right here on the screen, my solution trajectory, it will trace the solution trajectory. So if I click here, it traces the forward orbit and backward orbit of a solution trajectory. So this is going towards 0, as you can see, forward. If I am clicking here, it is again going forward, trajectory is again going towards this. So both the sides, when I started closer to origin, I am going towards origin. So that means origin is stable. Now if I see y equals to 5, now since my range here I have given less, so I am not able to see it, but let me put here 8 and 8. That will give us an idea. So now if I am closer to the so this is y equals to 5. So if we start here, the forward orbit is again going towards origin, backward orbit is going towards 5, and if I start from the top, backward orbit is going towards 5 and forward orbit is going away from 5. So basically convergence as such, we can see that this solution, let me go back and see the differential equation because I have a point here. Okay, that's what I was thinking. It's 5 minus y. Okay, so since it is 5 minus y, that is the reason it's not going towards 5, whereas our calculation showed us that it will go towards 5. There we go. Okay, now it makes sense. Okay, because the calculation was telling us if we are closer to origin 5, right, it will go towards 5. So when I clicked there, I saw that it is going away from 5, so I thought this is some problem now. So I went back and checked what is my differential equation. So it was 5 minus y. So now I can see if I start closer, it is going towards 5. And if I go from top, it is again going towards 5. Here, it's going away from this. So origin, basically, with this particular differential equation, origin is unstable and 5 will be stable equilibrium. Okay, but if I reverse the sign here, origin will become stable and 5 will become unstable. And why I thought, okay, some problem is happening, because when I was seeing the previous one, it was saying it is not going to 5, but our calculation mathematically showed us it will go towards 5. Right, so making sense? Okay, so this, you can note down this website and you can play around with it if you want to see the solution curve idea. Now coming back to this, and I will again revisit this website again to see the differential equation which we cannot even solve, how we will understand the solution of those differential equations. Okay, so is it clear to everyone that here y equals to 0 is unstable? And y equals to 5 is stable. Now by slope increasing, decreasingness also you can figure out whether your solution is stable or unstable, but I will get into depth more once we get to this topic. Okay, so now last time we already understand how to solve first order differential equation. So you have tried the homework. How many of you have tried working on the written homework which I gave? Okay, any question in that pertaining to first order linear differential equation? Now web work assignment due date would be, we will stick to the one which everybody can access the web work assignment right now, all the assignments with particular due date. Okay, we will stick to those due date. Now if the pace of the lecture, or we will see how the material is being covered, then I might change depending on it, but right now this is those will be the deadlines of web work. Coming back to the written homework, every week you have written homework. Tomorrow I will bring a written homework on physical interpretation and those things which I am talking right now, stable, unstable, and D field software which you can use, the same one which is basically we are recording right now. So that one. And from the first order linear differential equation, do you have any question in first order linear differential equation like this type of integrating factor technique? And if you have tried, then fine, we can move forward then if you have no question. Okay, looks like no question. Okay, so let's move to the next topic then, direction field. By the way, this homogeneous idea which I have here in this slide, it's not in your textbook, but this is one of the trick. Maybe I can say it very quickly here in this recording. Now y prime is this expression. As you can see, this is it a linear or non-linear problem? Non-linear. Non-linear. What's a method to solve non-linear differential equation first order? What's the method so far we have learned to solve first order non-linear differential equation? Separable. Can we use integrating factor technique to solve nonlinear differential equation? No, we cannot. So only method you have is separable one, and if the equation is not separable, you cannot even apply that. So that means you have no way to solve first order nonlinear problem. Now this is nonlinear, but is it separable? This one which is on the board. Why do you think it is not separable? Why do you think it's not separable? Is it separable? Tell me quickly, why it's not separable? Because? Exactly, very good. E to the power y over x makes it hard to get rid of these things separately. We can't separate it. Okay, we can't separate it, but if the equation is homogeneous, we can convert it into a separable differential equation. And what do we mean by saying if equation is homogeneous? If the slope has this pattern that if I multiply a constant in x and constant in y and replace it, somehow this constant get cancelled and I get back this function f, then this differential equation is homogeneous. First order. So if it is homogeneous, we can make a substitution here, y over x equals to some variable v, and then we differentiate both the side and try to eliminate it, and we get a nice separable differential equation by that trick. Okay, so this is a crux of it. So first we have to check whether the slope field is homogeneous or not, or homogeneous or not. So let's see here, f of xy is what? Magnification is too much. F of xy is equals to x square e to the power y over x plus y square over xy, right? So f of kx and f of ky will be, I will replace everywhere x with k, kx, and everywhere y with ky. Right now I am checking whether it is a homogeneous differential equation or not. First order, kx times ky. Now I can see k square can come out and this k can cancel, and k square can be pulled out, which we can get rid of that k square from the denominator. So which is same as the slope field f of xy. So that means this is homogeneous. Okay. Now if it is homogeneous, you will make a substitution here. Say v is equals to y over x. Or you can say, in other words, y equals to vx. Now y is a function of x and v has to be also a function of x. Differentiating both the side, you will get y prime is equals to v plus product rule x times v prime x. Right? Now y prime, we already know what is y prime. We will plug the value of y prime from the above differential equation here and make this change of variable. So it is x square e to the power y over x, right, plus y square divided by xy. And this is equals to v plus x times v prime, right? So now this one is v, so let me place everywhere. So I can make here v, okay. What about this term? How will I change this? Okay, everywhere just put v. Okay, x square e to the power v. Okay, then this is v square x square, right? Because y is vx, and then denominator is x times vx, and this is equals to v plus x v prime, right? I can take x square out, both the denominator and numerator, and get rid of that, right? Focusing here. So x square you can take out here and x square here. So you get e to the power v plus v square, and denominator will be just v. This is equals to v plus x v prime. Now you can see if I subtract v here, I am having a function of v totally and x v prime, so we can separate it, right? So e to the power v plus v square over v minus v is equals to, and you can, if you want, you can do 1 over x, and this is equals to v prime, and v prime is here dv over dx. So this is a function of v and this is x, and now you can separate and integrate. So you will get eventually a function of v, vx. Once you have vx, you multiply x in it to get your actual solution y. So this is a trick, that if a first order differential equation is non-linear and not separable, then you can see if it is a homogeneous, you can make this substitution, and this substitution will always work if it is homogeneous. If f of kx ky is equals to f of xy. So if that happens, if the slope field has this pattern f of kx ky is f of xy, then you can always make this substitution and change it to a separable differential equation. But if this is not, then you have no means to solve a non-linear first order differential equation. For example, if it is not separable, for example, you have y prime equals to x minus y square. Is it non-linear? Yes, because of y square. Okay. Is it separable? No, because we have subtraction instead of multiplication. Okay, so is it homogeneous? So if you replace slope field x by kx and y by ky, are you getting rid of k? No. So it's not homogeneous. So is there a way to solve this first order differential equation? Since it is not linear, we cannot apply integrating factor technique. So what we have to do here? By the way, we can never solve this differential equation. We can never write down the explicit solution of this differential equation. Now, since we cannot write down the explicit solution of this differential equation, it looks so simple differential equation, but we cannot. I mean, if anybody wants to figure it out and challenge me, that would be amazing. And I look forward to it. But I don't want you to waste your time. So it will not be. You cannot solve. Now, that's the reason we will approach towards seeing the solution locally. Global thing becomes much harder when you don't have explicit solution. And for locally, you can, because you have certain interval, you can write down the code or computation you can do and can see what solution is. But before that, we have to understand, will solution even exist for this differential equation or not? Okay. So in order for a solution to exist, so existence and uniqueness theorem by this theorem we can see that if the slope field, if f of xy is continuous, so let me write not CTS, if it is continuous, then solution exists. Solution will exist. If this function partial derivative of this f with respect to y is continuous, then we get a unique solution. And provided I should add here some initial condition, otherwise we won't. So if this happens, if we have this partial derivative to be continuous, and we are looking for this existence and uniqueness on an interval, on short interval. So that's the reason when I put a point here, I'm locally in certain neighborhood, I'm seeing whether the partial derivative with respect to y is continuous or not. If it's continuous, we get a unique solution. And if the slope field is continuous, then solution will exist. Okay, so x minus y square is it continuous? Now multivariable calculus. PDEs or ODEs, in both the differential equation, the only thing which should be very strong is your calculus. If you have a very strong background of multivariable calculus, then you can do amazing in PDEs. And if you have a very good background of Cal 1, Cal 2, Cal 3, then ODEs would be very easy. So here the reason it turned out you need some kind of multivariable calculus. So you remember when you have a two variable function, for it to be continuous, what were the theorems you learned? How did you check two variable function to be continuous? Remember from calculus 3rd, Cal 3, little bit introduction. So if there are two paths, if you are trying to check a continuity at a certain point, and if you approach from two paths and the limit is different, function is not continuous. But if every path you take and you reach to that point, the exact same limit, then function is continuous in multivariable. Now here I can see that x minus y square function will not have this kind of pattern. It will be continuous. It will not give a different limit with different paths. So this function looks continuous. I would not go into epsilon delta and proving it. Proving the continuity is harder in multivariable function, but showing that a function is discontinuous is easier, because you can cook two paths and you show the limit is different. Remember, depending on the slope m, you try with y equals to mx line and plug that back in the slope field, and somehow x gets cancelled and it depends on m, the limit, and as m changes, your value of limit changes, that kind of idea. So this one is equal, this is continuous, and partial derivative is just 2y, so it is also continuous, minus 2y, so it will be continuous. And partial, I am saying, full derivative is basically you will do the chain rule and all that, but partial with respect to y is just minus 2y, which is linear, which is continuous. Okay, so therefore solution will exist, and now it makes sense to even try and solve this computationally or whichever method we would like to. But if the solution is not, there is no point even proceeding. Okay, so that's the reason I'm giving you this theorem, that if the continuous, then solution will exist, and if this is continuous, it will be unique. Okay, so now we get to this idea of direction fields. if we cannot solve the differential equation, we somehow have to figure out how will it look like. So consider a region. So where you want to see the solution behavior, and we are focusing on y prime equals to f of xy equation only. We are trying to understand this one. Okay, so as per the initial condition, y at x naught is y naught. So that means if I consider a region nearby this point where this is, say, not origin but this is x naught, and its value of the solution curve here is y naught, and nearby this point I will place a grid and discretize this grid with a equal step size. Might not look here equal, but we are trying to see in this region how will solution look like. So all these points where these lines are intersecting, what I will do is I will compute the slope. So for example, this point I'll pick. At every point we will figure out x coordinate we already have, we will figure out the slope f of, so for at this point, say slope is f of x naught y naught, and like this we will find the slope at every point. Then we will draw a small tiny line segment passing through this point having this particular slope. So for example, here we will draw a line segment with the slope f of x naught y naught and passing through this point x naught y naught. Now there are so many bunch of points here, and every point drawing this tiny tangent line, and these lines basically will be what? Will be tangent to the solution curve, right? Because this is y prime is equals to this. And then we will draw our curve touching these lines, and that will be a solution curve. But is it feasible to draw so many lines with this particular, each computing the slope at each point and then drawing the lines at every point? What do you think? So is there any other way we can turn around this problem? Because somehow we need direction fields. So here you are saying it is very tricky, and that's is basically a definition of direction field. At a particular point you compute the slope and draw a line passing through that point having that slope, and all those bunch of lines are direction field. So now how we will handle this problem? So is there any other easier way? We don't want to draw every point a line. We don't want to compute, basically we don't want to compute the slope at every point. It is computationally very expensive, computing f of at every point in the grid. So what we want to do, what we should do, or we can do, so if we try to understand what we are doing at the point where we want to understand the solution curve, we start at that point, we place a grid at that point, and then suppose is this locally at this point I want to understand my solution, I will place a grid at this point, and everywhere I will find the slope, and then I will draw these tiny line segment if they are going like this or like this, but at every point I have to compute the slope f, right, at every point, or maybe like this. So I don't want to compute the slope at every point of this grid, and then maybe my solution would be going like this or in this track like this somehow. But I don't want to do this. So how will I get around with this problem? First step, find the points, and then we were finding the slope. And that's what we don't want to do. So what would be the backward approach? Finding so many points and then finding slope at every point. And that's how we are getting tangent lines. How about fix a slope and draw this f of xy equals to that slope curve. And then at every point you have a same slope. So then you are not collecting the points and finding the slope, but you are collecting a slope and then finding all the bunch of points xy for which this is a slope. Here I am collecting all the points and then computing the slope at every point. Now I am saying, okay, let me take slope to be 0 and see what are all the points where the slope is 0. Or what are all the points where slope is 1 or slope is 2. And that would be a lot of points. And that's how we can minimize this effort of computing the slope at every point in the grid. So consider this differential equation. And I think I will be able to complete this idea here. So is this idea clear to everyone? The main thing here. So if I have y prime equals to x over y. Now this is separable, you can solve it. The reason I am taking this differential equation is because I want to show you the idea where we can solve a differential equation so that we can compare it. What we are getting is right or not. Where we cannot solve, then there is no justification of it. And that's what you always do. When you write a code, you try to test it on a benchmark problem or a problem which you have a solution. And if that works on that one, then you say, okay, this is a justification, it would work on other things as well. So now coming to this point, f of xy is a slope and that's x over y. Okay. I will consider x over y, I will pick c to be as 0. Let's pick, so f of xy is equals to 0. That will imply x over y is equals to 0. That will imply y x is equals to 0. Okay, if I pick f of xy is equals to 1, this will imply x over y equals to 1. This will imply x is equals to y. Now what are these curves? These curves will have all those points which has a slope 0, right? So for example, if I try to draw geometrically this thing, so if x is equals to 0, right? So this line, x equals to 0. So all those points on this line will have slope what? What will be the slope of all these points on this line? What will be the slope of all those points on this line? Anybody? 0, very good. So all these points will have slope 0. So the line passing through these points having a slope 0 will look like every point, line passing through every point and having a slope 0 will look like this, right? Agree? So I don't have to compute then slope on every point. I picked a slope and drawed a curve, and this is called, so far this blue lines are direction field and this black line which is I drawed here, which is x equals to 0, is called isocline. This is isocline. Now this is also isoclines. So direction fields are perpendicular to isoclines. Now you will see now here, I will take that line back. Not perpendicular, but you get an idea of slope from them. Okay, so x equals to y. This line will look like how? The graph of this function will be 45 degree making, right? So it would be a line passing through this and making an angle 45. This one. This is y equals to x and this is isocline. Okay, now what is at every point on this line, what is the slope of that? 1. So that means, very good, so that means they are all overlapping it, right? Overlapping the slope of this. So they are basically okay, what will happen to if my slope is -1? Will imply x over y is -1, will imply x is equals to negative y. So y equals to negative x. Right? So now this one, x equals to negative y, will be this line. And all those points on this line will have slope -1. But see, now there is okay, so let's just draw them. They will also have -1 slope. So how will the solution trajectories will look like in this? Now if I try to go back and see my direction fields, okay, what will happen with an x is 0? X is 0 means y has to be, x is, so if the slope x over y can be infinity, right? I mean y equals to 0, then this slope will be infinity. That's not like defined later, I would not like pick that value, but if vaguely you try to understand, this is y equals to 0 axis, so the slope of every point on this line will be like perpendicular, right? It might be upwards, I can draw lines, or downwards depending on how we are going in the solution. So it would be like this direction field. Now you can see that this differential equation I can solve. It is y prime is equals to x dx, y dy is equals to x dx, which gives me y square minus x square is a constant. Hyperbolas, right? So that's exactly what I am kind of getting here is, if I am in this region, I will be moving like this. My solution, as my pen is going here, I'll start from here, I'll move like this. And if I am here, we have to figure out how the things are. Here it will be going downwards, like this. If we go back to the direction field software and see what is the direction fields doing there. So y prime, what was the differential equation we had here? y prime is equals to x over y, right? So I should say here t over x. So you can see if I start it here, I make this rotation, right? So perpendicular here. If I start at the bottom, I move like this. Now these blue lines are direction fields. And same you are seeing in this PDF. You move like this and then you get tangent to it and you move further. So this is what I was saying. You go like this solution curve, then it gets tangent to it and it will move like this. And if you are here, you go tangent to this and you move down. Now they don't cross each other, so I cannot cross this line here. What happens in here, as you can see from this, it's kind of repelling here. You see, here it is downward, here it's upward. So if I go in this direction, then it's this, otherwise it's go downward. But anything which is up here or here, we will get the direction fields. So you can see that picking a slope, drawing an isocline, and then collecting all those points where we have this particular slope is much easier than picking the points and computing the slope at every point. We don't have any idea that we pick this point, slope is something, then another point something, and there's so much variation in the slope from there to there. But we pick like kind of some independent axes and try to give a feel of whole plane. So if I have taken here minus, this is an exercise and you can try it out, y prime equals to negative x over y, then you will get circles, right? Because you get a plus sign here. So your direction field should then create circles. So you can try on the same line, picking the same slope, 0, 1, minus 1, and undefined number, infinity. So these are the isoclines. All these graphs are isoclines. Blue lines are direction field, and red dotted line is solution curve. Now depending on initial condition, you will start from there and then you try to trace the forward trajectory of solution curve. It's up to you. Backward also you can trace it. So forward or backward orbit we call of a solutions. But right. But this is how you would proceed for the equations which you cannot solve. So now coming back here, if I try to write down here x minus y square I had, right? So t minus x square. In this differential equation I see there is so much pattern here, and it's kind of a funnel that it will be trapped in this region, and wherever if you're outside, then solution, and you can see solution trajectory, it might seem here they are touching. No, they cannot touch, they cannot cross. Why they cannot touch each other, or why they cannot cross each other? If they cross each other, what will happen? If you are really listening to the lecture, you can give me this answer. If they cross each other, you will have two slopes at one point. That is true, but how is that like not possible? And why? What will basically be initial value problem if they cannot cross each other? If they cross each other, then what will happen? You will not have a unique solution. because then you will say, okay, I will pick this initial condition, but where will you go? If they touch each other, then which trajectory you will choose at this point? If you take this point as initial condition, and if they touch each other, then you are in a confusion, should I take this or should I take this? But if the partial derivative of f with respect to y is continuous, then you will have a unique solution, so that means your trajectories will never touch, will never cross each other. And this software might say, okay, they might be touching, they might be crossing, no. So sometimes computation will not tell you all the depth of a differential equation, and reading certain book will tell you. So there is one book which I used to read a lot, and you might also, if you can get from a library, has a good theory. It's not too many examples, but theory, understanding. And examples also are there. They have solved examples, but they do have a nice theory to understand. They will not touch, cross, and those kind of things. So Shapley-Ross differential equation. I think maybe it is Shapley-Ross. So but if you Google it, you will figure it out. Okay, what time is lecture over? 1:10, right? Okay, that's it for it. And give me back the sign and sheet. Okay, this is the one.